I'd like to, well, Terry has introduced us, so you know who we are. I'm going to take you through a bit of a train of thought that we have been developing over the last 6, 7, 9, probably more years in a similar way that you've been doing. And I'm going to run through some early examples very quickly, and then take you through to some of my early conclusions, and then pass you over to Christian. Perhaps it's worth saying that the R&D group at AEDAS was founded in 2005? 2004, wow. And since then it has changed its profile in many ways. But one of the things that has been really consistent about the work that we've been doing is that we have always had a big focus on feedback. And I'm going to talk a little bit more about that later, but just obviously the whole publication that Terry's been editing has been very much about that. But our sphere of expertise was very much based on computation, which computational design, which Christian is leading, and sustainable design, which I took a very strong interest in, and construction and fabrication, which is something we both really are interested in, and we are always ending up working somewhere in between. And the most interesting bits of work that we have done tend to be in the overlaps of these. And a very, very early project that I did many years ago, which was the Dubai Metro geometry. And you must have seen perhaps some images about this project, but certainly parametric modeling is my sort of background, architecture and parametric modeling. And Hugh Whitehead, who is sitting in the back row, who's been a very great mentor, would probably see a lot of influences in that. And that was a project we worked on in 2006, and since then we did a lot of work on building envelope. And you'll see from these examples, certainly the allure of a sculptural form, and then looking at how that performs has been very much at the focus of our early work. But what you find is another example where working in Saudi Arabia, in Saudi Arabia, we were working on a tall building, wanted to make the facade in a form that actually draws the prevailing winds into the shading system, because doing double skin facades in the Middle East is a bit tricky. And just beginning to work these sculptural aspects into the building envelope itself. We also wanted to look at solar radiation and actually drive the distribution of percentage openings around the building facade by the amount of solar radiation that particular facade is going to be subjected to. So that was a building in Abu Dhabi. And when I worked on the Karachi Port Trust Towers, it was the first time I actually really wanted to know how much are we really saving by all this effort. So we were making a huge amount of design effort. Are we really saving anything? Or is it really that we're just adding to the character of the building? And if I go back one slide, the thought that a parametric model can give you feedback about wind performance, can help you optimize the geometry, structure your data in a helpful way, you can do your environmental analysis, as well as your physical prototype. So, 5 years ago, this was quite interesting. But being able to tell that it was going to save us 15% of our CO2 emissions was actually quite forward-looking. Albar Towers, which is due for completion this year, was quite a bit more of a challenge. And you will see from this animation, again, using the parametric tools to structure the data about the building geometry, its efficiencies and the rest, so that we can output this information for smooth production. We would have never been able to get away with building this building without the pure geometric control of the shape and being able to communicate that really fast. So I'm sure many of you have seen these types of parametric models since, but it was certainly a big step to actually produce the building, to drive the fabrication process from this model. Again, the thinking behind the building was that or the design was that the client very much wanted a transparent facade, and or a glazed facade, and we were very keen not to end up with a glazed facade which is black or very dark, with highly reflective, so that you have to turn all the lights on. So Abdul Majid, who was the lead designer of this project, Abdul Majid Karanu, a colleague of mine, has gone to a very large, to huge lengths to make this happen. He's come up with a louver system, a geometric louver system. You'll see in the corner the little animation of the prototype there. It actually changes shape depending on the solar angles. And what you see here is the aesthetic effect of, I don't know if you can see down here, you can actually see through the mesh really quite clearly, whereas when you look at it from the outside, that looks actually rather solid. And some of the recent pictures from the site. The animation is not running yet, so. So one of the thoughts that we had at the time, okay, if we do invest so much effort into the building skin.
Water.
Some water. Sorry, I've got a cold. We would really like to have feedback, not only about the carbon emissions of the building, so the energy consumption, but we'd really like to be able to contrast that with the embodied carbon, which is the bar that you see down here. And then we would really like to see how that compares with the capital and the whole life cost. And we've devised a model which is we've shown a few times before, which is the parametric tall building model, where you can change things like the floor-to-floor heights, the facade specification, the complexity, the lighting strategy, the occupancy, the set points, etc., and get very rapid feedback about all of these factors. And it was a collaboration between Davis Langdon, ourselves, Arup, and Hilson Moran. And what you saw there was actually, we had to map the complexities of all of these disciplines together. So imagine that normally when you make a model, you send it off to a consultant, you wait for the response, that comes back. By the time it comes back, conversation is over, decisions have been made, and it's quite a bit more expensive to revisit those points downstream. So we wanted a model that will give us this ability to make early stage briefing decisions much faster, and that's so you can put in the footprint. The model then generates an extruded shape, which you then get the usual outputs for, and it's based on real quantities. You can change the shape of the building, change the height of it, and you see all of these parameters update. So you get an idea that proportionally, for example, if you add perimeter daylighting, you can reduce a certain amount of carbon emissions per annum. Doing the glazing performance by orientation rather than having the same cladding all around the building, occupancy, the cooling set point. What was really interesting to me is when we actually incorporate what we call unregulated energy, or some amount of unregulated energies, which is appliance loads, you can save a hell of a lot more. And then the value model. So someone who is developing such a design for sale will be looking at very different indicators than someone developing for an owner-user, as many of you may have come across that. And then when a project is funded by government, the most important aspect of the most important driver should be what sort of additional value does that building bring to its neighborhood. And very often, that was good. And very often, when we work with clients who are developing for sale, we're trying to bring more of that downstream value into the project. And we did a very interesting project with Stuart Lipton from Chelsfield, with the same partners, evaluating the whole life aspects of different systems. And I'm not going to talk too much more about this. But easy answer. Which system is basically the most, has the biggest advantage in terms of occupant comfort, adaptability, net area, capital cost, whole life cost, embodied carbon and operational carbon. And we're really beginning to set up this workflow as a result of these projects where we can evaluate these aspects much faster than we used to using computational and other techniques. And yeah, so the role of feedback. We do that obviously at a project level using these tools to inform the teams, so to make decisions a lot quicker, then disseminating this work across the practice, and then also working with organizations outside the practice, with government bodies and SIPSI, RIBA, and other organizations. You'll see the research projects that have arisen out of this kind of line of investigation. We're working with the EPSRC and the Technology Strategy Board and University College London on virtual information modeling, carbon management in design and construction practice, climate change adaptation. And I'm going to talk about a couple of these. One is going to be carbon buzz, which came out of this really intense focus. The incredible effort that we put into these buildings to achieve real low carbon performance, does that actually happen further down in once the building is complete? Having set up this platform in 2008 to allow people from both the architecture and the built environment profession, the broader built environment profession, to gather and publish data online, what you can see is that buildings in general, the compliance calculation or the initial estimates over energy consumption tend to be less than a half of what the buildings tend to actually emit in terms of carbon in operation. And that was quite a shocker, because we do all this work on different parts of the building, but how can we really gauge whether overall that's what really matters, and how accurate are our assessments and predictions? And so one of the focus points of the Carbon Bus project is to identify the risk areas that really stop buildings work in the way in which we expected them. And for compliance, what you do is you look at a building and you benchmark it basically against a building which has fixed operating hours, fixed number of occupants, with a very specific building fabric. You ignore everything about what happens downstream, i.e. is the contractor going to do install the windows that you specified? Is your air tightness going to be what you expected? Is your ground source heat pump really providing 40% of your heating, or only 2%, as we have seen in some examples? And then you add on the IT and the plug loads, which we always omit. Then any special functions, as Bill Bordas would say, the Large Hadron Collider in the basement. And the real how many hours are people really going to spend in this building? I bet you that in this building, for example, unless you got chucked out at midnight, I'm sure some people tend to spend a few more. And how do you design and how do you plan for these factors? The very last one there is building management, which is this little icon. And we have engaged with the Technology Strategy Board to monitor now up to 9 buildings in quite a lot of detail, and some others in just short segments. And for example, Darwin Academy was a really short study. The predicted versus the operational energy consumption is not too different, but you will find that if you just do a very short study of a building, it's really hard to establish where the energy is being spent. Is it spent on heating, hot water, cooling, lighting, process loads, or the rest? We would like to get to a point for every single design project in the practice where we establish this prediction a lot more accurately with all the risk factors attached, as soon as possible in the design, and work with our clients to mitigate those risks. Another building, which is Loxford School, you'll see that the prediction was a fraction of what we ended up in operation, almost 3 times higher. Some very good reasons for that, including the ground source heat pumps, which only supply 2% of the energy. And then how you communicate this information to school children. And I just put up this slide because it's a completely different type of conversation that you would have with building occupants. And you were showing some of your engagement work. It's really fun. And another building where we actually got it right, Pool Innovation Center, which is up for a couple of awards. The prediction, the actual operational energy use is a lot better than what we thought. We had a fabric first approach. We were really working together with the design team to get that those risks ironed out early on. And this building, which we have recently started on site with Keynsham Town Hall, it's going to be the first the first A-rated operational energy use building in the UK, which we're really, really proud of. I know it doesn't sound that exciting, but what's really, really fun about it is that when you have an operational target rather than just a compliance target, you begin to work with your engineers, with your clients, and with your contractors in a completely different way. You share information, you share cost data, you share whole life data. And in this case, it was we had a relatively easy time because we worked with a client who was very well informed, and they were the end users. It's much more difficult to do this when you work on a speculative project. And you've heard me talk a lot about carbon, and Christian is going to talk about other things, not just carbon, when I let him put a word in edgeways. But the value of low carbon buildings, we know that regulations at the moment and design standards don't really contribute to the building's actual value, so market value. But we don't know whether that's because the badge doesn't help, or because we haven't actually achieved operational energy, low carbon energy in use. So most of the buildings that we are looking at, that we're studying, and also the building performance evaluation program is looking at, shows that the discrepancy between predictions and operation is really, there is a really large gap there. And so this thought of thinking about buildings as more of an ecosystem of fabric, services, equipment, with the occupant, the user at the center of this. People do completely unpredictable, unexpected things in buildings, and we just have to build structures that are resilient to cope with that. One of the things that a group of architects came together as part of a big event at our practice was we all thought, well, we must be able to design out building management systems somehow. None of the education buildings that are being studied under the building performance evaluation program have a building management system that really truly works, which is a bit of a shocker. So I'm going to leave you with a little animation, if it comes on, about doing things that aren't necessarily just about energy use, but studying what... this was a little sculpture we did as part of last year's Smart Geometry program with Josh and Peter Feldman and lots of other people in the group, where we monitored the level of activity, so the intensity of the activity in different workshop clusters, and these things change shape based on how intense those activities are. And that's it. Sorry, Christian. Over to you. They're very patient. They're very patient.
Let's see. We have to... It's okay.
Judit.
So according to schedule, I've got about a minute. Let's see if I can bring it into 30 seconds then. It's for me also interesting sometimes when you and I present together at the same location to see what we're both doing. Because we have slightly different approaches, but they're of course actually complementary, which you see maybe in the last application, which I will show. But up to then, I'm rather talking about maybe the idea of a place or a building or geometry can be seen as an ecology in its own right. If we think about ecological design, it doesn't necessarily have to be about energy. So the computation design side of things contains at the moment 5 people, and who's not here, Azam Gamnesette, Lucy Helm, Praten Jaganat, and Anders Holden Dilleran, who are not here. As you maybe have seen in the article, I brought this in because it was mentioned in the article. This idea of feedback is of course an old one, more from the 60s and 70s, where the idea of ecology as well and feedback derived from completely different understandings. It was more the understanding of one thing affecting the other. And as Maruyama would have it, he kind of coined this term deviation amplification, which means that if one triggers something, it amplifies it somewhere else and then re-triggers it back. So it's a mutual response. And von Förster even went as far as saying that the whole set of realities is this idea of many feedback loops affecting each other. So feedback in the sense that there's an ecology of feedback, an ecology of relationships to each other. In an architectural sense, in a built environment, you could see that not so much always as the idea of system of structural systems, but in our perspective, or the way that our focus is the idea of the configuration of space and what's the ecology of the configuration. And I mean ecology here because not just do we have a lot of theory about the idea, amongst them here in London, of course, in the UK, Bill Hillier with the idea of the syntax of the space, or as you described it, space the machine, all based on the all behaviors within the building are more or less down to its configuration, and the configuration or the behaviors are mainly based on movement or permeability structures. Initially, before Hillier wrote Space the Machine and then Sociological Space, they actually wrote the space syntax paper, which was meant to be a generative theory of design, and all based on a type, or actually on 8 types or 9 types of syntaxes, which all have to do with how to configure spaces as a mutual, or they call it as a dual representation between people occupying and producing space, and a space affecting people again. So this idea of Maruyama, of that feedback, that's not necessarily explicit in design, because we can't necessarily design this feedback. We can only understand it ahead of it. Try to understand it. So it's an activity or occupation-based ecology, if you like, between the geometry itself and the user. And what that produces types of local phenomena which are dependent on a global performance. A global performance is dependent, according to a configurational theory anyways, to the permeability structures and how you get around and what you see when you go around. So it's becoming more and more intense, of course, nowadays, more rigorous. In the sense we're not just looking at movement anymore, but also other types of perceptive qualities of space. So we're going as far nowadays as being able to simulate some of Kevin Lynch's mental mapping through associative maps that we're sometimes using for more like narratives of planning, which I won't be able to show here today. But in the planning environment, it's quite interesting that the UK especially, I think amongst one of the few countries in Europe, or maybe worldwide, I'm not sure, has gone away from the idea of writing design codes as rule sets. But they've meandered after the disasters of the 60s and 70s, where it was very parametric almost, to the idea that you actually specify guidelines for what they call principles, or as the by design guide would have it, planning objectives. And how you then actually implement and how you arrive at these planning objectives or these design principles are often, it's not very discursive, it's not very explicit. So hence I showed this image from the guide on the right side, which is a very non-discursive performance that they mention, but there's actually no way you can actually just parametricize this. So you have to actually think about how does this idea of the feedback here come through maybe the simulation that you're running, not just through everything that you specify ahead of time. And the ecology of space, therefore, or place in that sense, these qualities, are actually very much down to these principles, not to quantities. And we experienced that once firsthand, and it gave us a little bit of a shaker in 2007 when we did this project for Urban Buzz called Smart Solutions for Spatial Planning. Beautiful name. Not very good. But we worked with various planners, regeneration officers, and urban designers. And initially, we were, of course, very enthusiastic. We can simulate plot ratios and routes through site, the centrality, how much they traveled on, and where the footfall may occur, and the access strategies, how far it is to different amenities, and the scale, therefore, of the buildings or the local fabric and the density, how much it should be, and pour it all, integrate it all into one application, which then give you a massing, right? And we could only see when we proposed this and we showed it then to our partners at the time that they only raised eyebrows in the sense that either we believe your simulation that has actually calculated all that correctly, or we don't. But for us designers or planners, in that case our partners and us designers as well, it doesn't really help us if we actually have everything integrated into one big simulation, because then we can't interact with it anymore and we're not part of the ecology, if you like, part of the system that actually tries to arrive at some place definition. So in other words, these principles that the urban designers or planners talk about have been occluded through over-integration, I would just call it. So what we arrived at was to say, okay, we need to really break this down and design the applications or our simulations also in such a way that it becomes very evident what the simulation is trying to do or how it struggles to get there. Hence we broke it down, for example, these slides just into these actually 6 to 8 applications came out of it instead of one. And the planners were a lot happier, and the architects and urban designers who work with it from then onwards have really picked it up. Otherwise, it may have seemed like an academic exercise trying to simulate London for 2050, and with very bad kind of intellectual or intelligibility of what this is actually performing. So ever since we're extending our what we call it on the one hand, so the digital master planning platform. On the other hand, is actually sort of a framework or platform of many very small parsimonious simulations that only ever try to do one thing at a time, never more than one, because then you don't see the purpose of the application and it's very difficult for design to participate. So at this point, because I only have 1 minute, I'm just going to go very briefly into a couple of, well actually I've written down 5 applications, but I can only run the application. I don't talk about the project, so that you maybe get a little bit of an inkling. So from a, for example, movement perspective, we wrote a series of applications at the time already in 2007 and 2008, where you can, for example, we were then being approached by Crossrail consortium after they've seen what we've done, because they realized when they usually work with their consultants about routing and pedestrian flow, all they get is tables and access, so footfall at certain points. So what we try to do then is actually use some of these algorithms that we work with and riddle it down to one type of behavior. And you can see here these were actually station entrances, so they had to try to find out in Whitechapel where the entrance should sit. And these are so the sync points, meaning where people go to, and these were from interviews that we conducted on site where people come from during the day. So we're doing the observational studies ourselves. And you can then see maybe from certain points, where people come from, you can then seed them, you can give them how many points they need to be. The colors indicate the distance, the width indicates the footfall, and the lines themselves are calculated by different types of criteria. So this one here would be, okay, if you're in the morning, everybody knows the site and there's rush hour, everybody runs to the access point of the station. These would probably be the shortest routes, i.e. how is our urban environment then occupied by choosing these locations for the routes? Or which entrances, as you can see, are not relevant, so I can actually take them away. So if, on the other hand, this is Whitechapel Market, during the daytime, we're going to actually have a lot of tourists coming in. They're going to use different routes. So of course, at this point, I would actually have to find new ways of placing these departure points. But the routes become actually different types of definition through the environment because of the way that we read space the first time we go through it. So it's called a perceptive depth rather than a metric depth or distance. So you can see how the city is going to be occupied differently from that type of scenario during that type of day. And sometimes I just like doing this for fun. You can see a little bit, it's potentially interesting that the complexity that we always talk about, can actually be somewhat seen, if you like. If you actually then see the structure of the space, you can also see the relationships between the entrances. There's not much going on over here, depending where I place them. And I can see how my whole city changes its occupation. We take that then into, of course, you can do that in 3D. So we did that for Mazda in 3D because people need to be walking in cool spaces rather than hot spaces. But what we're trying to do more from a perceptive point of view in using the space, we're also then analyzing, once we have looked at the routes, we're then trying to find out what people see as a walk-along routes. So this is again a simulation. None of this is ever recorded, what we're doing, so it's always live, in order for you to be able to interact with it and work with it. But what happens here is also, you can see, this has several consequences. What happens underneath actually building up a gradient map to show you what is being seen, how often, which building, which elevation, for wayfinding, but also for allocation of land uses. For mainly these 2 points, but also in this case it was very important for informal crossings, where people would actually like to cross the street rather than the crossings are allocated. So again, it becomes a whole series of issues that we break down so that you can actually see the calculation or the behavior of the application, if you like, in that sense. This can be then transported if you want to go rather abstract, which is currently not really the case yet, and we haven't really used it too much. But you can see something like this, where you can then try to understand so this is a post office building in Sweden, and we start to analyze what groups of people, according to distance, what they see, if they see each other and how far they sit away from each other, and how they get to each other by different types of route evaluations. So in other words, 3 types of behaviors, how they can actually, what types of groups might actually be interacting with each other. So nowadays in workplace consultancy, and there's some guy sitting here all by himself, so it's not very well placed. If you have certain radii that is of interaction that you need to adhere to. And what's also interesting about this is that you actually get completely, this wasn't so successful here. I need to get a different cluster for that. That you also get a different type of, how would you say, how the building is mentally partitioned. That's what I mean with Kevin Lynch in that sense. We can actually try to get to some of the criteria of behavior and perception that make us understand how we think the building is partitioned. Is it vertically partitioned as we see in plan, or actually other horizontal, other pockets in the building that we don't see in plan, but they derive from other behaviors that are not purely in the geometry. And these types of projects can be taken forward. We just did a more speculative work for a German research institute, where we say if you take these behaviors into account, and if you actually had to plan a space from inside out according to these behaviors, you can surely find some algorithms and some ways of planning where you take the movement structures into account first, and your functional areas being able to carve out around that. So we can actually see how the movement structures in 3D are trying to bundle themselves quite literally into groups, and you can see where actually what we programmed in a certain amount of areas and certain flows of paths come together, where there may be additional unplanned spaces that can be occupied in a hybrid sense. So you see that quite a lot, where people meet, they may actually set up a shop or something like that, right? So we're actually starting to figure out where these unplanned activities might occur. So once you have your movement structure, you're going to get, of course, a partitioning into the functional areas, which are actually more or less here achieved, as you can see, the areas you need to target for. Not all of them, some of them actually over. So you need to then, of course, start to work away at this, which you can. You can just work in here, you can actually add spaces, you can copy spaces, and So you can do it actually, oops, come on. Maybe I'm not very practiced anymore at this at the moment. This was obviously, as you can see, for laboratories. Yeah, now I've got my new laboratory space. I can link this up, and then I can tell it to be on a different level if I correctly do it, and then I can link it up with other spaces, and slowly but surely build my network between here again. It doesn't come on now. But what we see then slowly, we can actually see the subdivision, different types of spaces, and how this develops from a type of movement angle. Equally, you can do that then inside if you're looking at a single floor again. They're using these movement logics, but based on other types of behaviors as well. Here we've got a furniture grid, and then you can work while you're actually inside this already proposed partition by still manipulating actually geometry as you're inside. The reason why I'm saying inside is because we had they weren't standalone, they were all linked up to a virtual environment. So you were actually not inside a cave, you're tracked with goggles and you were inside that space. So as you were moving through, it would actually sense where you are, track you through the space, and you could then say, I need more space here and less here. I can't understand why there's this this path splitting here. Where is this going? So you could actually you could occupy it and design it while it generates at the same time. So all of these bits and bobs, going back to some of these ideas of building these ecologies from various different aspects, and I showed you just one or two now, from movement or permeability and visibility, into this idea of building them from inside out with a certain behavior of the designer being able to bring himself in rather than being at this massive simulation that you weigh. Then can also sometimes just be quite nice from a visualization point of view. We did this more back to a carbon measuring device, if you like, for Barclay bikes. We got the data and did this visualization about at what point in time a bike was picked up, where, and where it was dropped off when. And then we try to visualize how the city would be occupied because of where the docking stations would be allocated and how people use them. And you can see here an overall integration of what the main travel routes over time were, and where there's obviously a heavy load of bikes going through. But we also simulate in a way that you can just see it per minute over 8 months, as you can see down here. And you can see how London's being occupied by these bicycles according to the data that we got from Barclays and intensity of use. And then you can see at what time of the day, of course, how it is occupied, and overnight and then it becomes a bit calmer. Evening, rush hour obviously. Is it sunny? Is it rainy? You're going to get an indication for this. It's coming down now in the evening. You can see where the stolen bikes are because they're never returned. The line always stays on, and you can then start to propose now design interventions from here as well, because you start to see, you can start to calculate basically which docking stations are little used, which are much used, along which routes basically is a heavy cycle used in the city. Should you have different uses along them? Like, should you have actually a bicycle repair shop there? Or should you actually deviate it if it coincides with a large road like Oxford Street? So you start to have some information about, in that sense, again, the ecology, more of a feedback between the geometry of the city and the use of it, right? And between how we can read it and how it offers itself to us in order to design through that knowledge. And I think, oh yeah, sorry. And here we did the carbon counting, of course. You can see down here we measured then how many kilometers, and of course have been traveled over time. You can then also count this per hour if you want, so it gets a bit more intense. And you see how many I think it was kilograms per carbon by other means or modes of transport would have been used if the bicycle wasn't used, or if the scheme wasn't in place. At that point we found out that the over 8 months or 10 months, whatever it was, the use of this scheme has only reduced as much carbon as a single office block in London would produce. Yeah? So it is quite interesting that we could say that there's a problem that we think we have these placebos sometimes in place. So, oh, a cycling scheme, we're green now. But we can also see that it might not, I mean, this is of course just an approximation, it might not be as beneficial as we think, or it is very beneficial obviously, but that compared to other emission objects, so to speak, it's quite innocent, or ineffective. And that's where I leave it. Thank you very much.